hide self-view. That's what you want to do, hide self-view. And all of this takes away, distractions from the main screen. So if you can just hide self-view. I don't know if that only hides it for you, but anyway, welcome to our meeting for March 1st. We are very honored to have Anders Sandberg coming to speak to us, and he is going to talk about something that only some of us may have heard of, and that is, I hope I'm recording. Do people see the record button going?
Yes, it's going.
Okay, I'm sorry to interrupt my own self here. He will be speaking on a theory that is not familiar to everyone, but it should be, because it has the very beneficial function of taking us out of the pre-Copernican and geocentric. That means that only Earth is important. It definitely changes that, and there are a couple pieces of literature that change it in kind of a fun way. But I'm going to mention one that's very influential before Anders comes to give us his studies on the rate filter theory, and that is H.G. Wells' The Time Machine. And for Victorian Londoners or people in the UK who were his main readers, they had never even thought about the possibility. They were discouraged from thinking of the possibility that humanity might not go on forever. And it's a strong possibility. In fact, it's the reality, because either we'll leave this planet or we won't go on forever because the sun will die. Now, that may be hundreds of millions of years away, so most people don't get that disturbed about it. But when the sun dies, humanity will not be able to exist on this planet. So that was a new idea. And I don't know, what was it, 1892, 1894, when the Time Machine came out, and people found it very upsetting and something they'd never thought about before, because they'd always been geocentric. They always just limited their thinking to the doings on Earth. A later story that did a similar thing was Isaac Asimov's Nightfall, and that involved a planet where night only happened once every 2,000 years. And so when it was coming, people were terrified because they'd never dealt with it. They didn't know what it was. It was a configuration of suns, 6 suns around Lagash, this planet, that were mutually lighting each other, so that's the reason, it's complicated, but that's why they only had night, when they would have eclipses enough so that night would happen. So anyway, people had to suddenly think there was something outside of Lagash, and they'd never considered that. So the astronomers and the religious leaders were each explaining it in their own ways. And that's another good story to read about suddenly having to realize that it's not a geocentric universe. And so with those two, I will get back to Anders. Anders, I know you've been at Oxford, and I know that you're the head of a foundation about Earth's futures. And so I know you've been thinking about these things a long time, and perhaps you can share some of your very deep thoughts with us. And with that, I will turn it over to you. Oh, and you probably do you need slides? Okay.
Yep. So I would like to share
yes, and I have it set to multiple people can share. So just pop your slides right in. Or you just hit share screen and then open up your whatever you have, PowerPoint.
So let's see, you might be. Yep. Okay, so thank you so much for having me. So I am one of those unruly students who can't keep to one topic. I drove my professors nuts by not just studying the computer science that I was supposed to do, but getting into virtual reality and studying a bit of Latin sounds fun. And neuroscience. Yes, I want to work on neural networks. And then I ended up in the philosophy department at Oxford University at the Future of Humanity Institute. And throughout the 19 years the institute lasted, we were working on questions like, well, what is the fate of humanity? And can we do something good about it? So this is going to be linking two threads of our research that at first look like they're very different. On one hand, there is the question, is there extraterrestrial intelligence? And the other question is, what are the threats to the humans and the species, and where might we end up? And of course, they're not separate at all. They're quite strongly linked. And the classic core question is, of course, the Fermi paradox, or the Fermi question. So back in the 1950s, literally in the canteen at Los Alamos, where the nuclear scientists were having conversations about this and that, somebody had brought up an issue from the New Yorker magazine about an article about where are the waste baskets in Central Park going? Maybe it's little green men that are stealing them, because they're certainly disappearing. And the physicists around the table were talking about the possibility of intelligent life on Mars or elsewhere in the universe. And this was the 1950s, so atomic rockets were clearly on their way. So going to space, everybody agreed that was doable. Going to other planets, yep, an engineering challenge, but nothing we couldn't do. And then Enrico Fermi, the great physicist, just chimed up and asked, where is everybody? And there was that moment when everybody realized around the table that this is a profound problem. After all, the universe is really large. The Milky Way has about 300 billion stars. And although in the 1950s it was unclear how many of them had planets, it was very conceivable that there would be planets around most of them. And of course, there are other galaxies. Also, the universe is really, really old. Again, in the 1950s, it was a bit unclear, but the main contender for cosmology said the universe was infinitely old. The Big Bang theory was still kind of nascent. So this leads to this annoying realization that would emerge. And then it probably wouldn't be able to travel around or send signals or do things we could notice. But we don't notice anything.
May I just interrupt? I hate to do this, but could everyone take your video, turn off your videos and your sound? I'm going to do it myself. Sorry.
Yeah, sorry if there is anything interrupting the picture or anything. Yeah. Anyway, the Fermi paradox is not really a paradox as philosophers would like to describe it, because a real philosophical paradox is where you have something that is intrinsically contradictory. But in this case, it's a tension between our experience of the world. There are no misparked UFOs. Central Park's waste baskets are most likely not stolen by aliens. And the theory we have about how the universe works. If you have enough places and enough time and some reasonable probability, there should be a lot of alien intelligence. So something is really odd here. And the reason we got interested at the Future Humanity Institute is, of course, that this is information about the fate of civilizations. If the sky had been full of alien civilizations and maybe ruins and the things they did, and we could observe it in a telescope, we would gather statistics about how it's going for intelligent life in the universe, and it would give us some information about our own chances. Instead, we see just this silent, ominous sky, and that seems to tell us something. But the question is what? And this is also where things get interesting from a philosophical standpoint, because absence of evidence is not evidence of absence. And even when you have no information, the fact that you have no information might actually tell you something profound too. So this is juicy for philosophers and scientists who like philosophy. And of course, people have been trying to answer the Fermi question in all sorts of ways. So we have this is just a short list of proposals, mostly limited by the font size I could get to work in PowerPoint. And one group of answers is, of course, yeah, there is nobody around. And one possibility might just be that intelligence is short-lived, and that would be very bad news for us. Another possibility might be that actually intelligence is really rare in the universe, or we are even the first intelligence. That's kind of good news for us. The universe is ours for the taking, or at least a sizable chunk. On the other hand, it's also this awesome responsibility that maybe it's up to us, oh dear, to be responsible for its future. There is also explanations that say, yeah, actually, we haven't been looking in the right places or in the right way. And maybe it's actually hard to observe civilizations. Maybe it's harder to travel through space than those atomic scientists believed in the 50s. Or it might be that in the past, there were so many supernovas and gamma ray bursts that most life always got kicked back into the oceans on most planets. So it's only now when the Milky Way is starting to become a bit middle-aged, when things quieten down enough that evolution could take hold. And that might mean that there is a phase transition going on, but up until now, intelligence was very rare, but now it's kind of waking up in different parts of the galaxy, and we're eventually going to meet the others because there is a phase transition going on. It's a really cool theory. My friend Milan Surkovic has proposed it in a few papers. I don't think it works because the distribution is too broad. And then, of course, there are various explanations that are really good story material. Some of them, like that, actually, there is intelligence out there, but we don't even recognize it as intelligence. Maybe like Stanislaw Lem's Solaris. Or maybe they change in interesting ways that make them impossible to see. Maybe they transcend the physical universe, or maybe they're sitting quietly in enormous data centers somewhere in the galaxy and playing the alien version of World of Warcraft. Or maybe, like Carl Schroeder proposed in his novel Permanence, they devolved to a post-intelligent state. Or maybe they're already here. Maybe they're hiding from each other. Maybe they're actually watching over us, but follow some form of prime directive, much better than Captain James T. Kirk ever did. Or maybe we're inside one of their simulations, or maybe actually we're secretly talking to the president. Sorry? Was there any question?
Someone doesn't have his microphone turned off.
Yeah.
Is this the new person who just came in, John Ryder? Please turn off your mic.
Yeah, no problem. Anyway, these explanations are interesting because they're both very interesting theoretical questions about the world, and many of them, of course, make for very interesting stories and might tell us something about our own chances. When it comes to communications, I think in these days people believe that we can actually deliberately send messages over a sizable chunk of the Milky Way, not an enormous one. It turns out that the radio waves that the classical search for extraterrestrial intelligence was looking for have this problem that in the electromagnetic environment of the galaxy, they tend to spread out and get scattered. So actually broadcasting radio waves over very long distances is surprisingly tricky. But it still might be doable, and we have certainly sent out radio waves, of course, from Earth, which are probably hard to detect more than some tens of light years away. But more recently, people have become very convinced that laser communication is way better, and it's not terribly hard to focus laser beams on interesting stars and send them over much longer distances. There is also the interesting possibility of actually sending out probes. So the Breakthrough Starshot project was looking at using lasers to accelerate light sails to get to nearby stars within a few decades. It looks like that is actually a fairly realistic prospect. It's not a good way of sending explorers there, but we could totally send at least the postage stamp size microchips and other systems. And once you get to a more technologically advanced level, of course, going out and settling the Milky Way, if you can settle nearby in solar systems and then wait a few thousand years and establish your civilization, and then go to the next system, within some tens of millions of years, you have settled the entire galaxy. Indeed, one famous paper in this debate about extraterrestrial intelligence is titled Alien Intelligence Doesn't Exist, or something similar, by Frank J. Tipler, where he points out that if you can do this kind of settlement, it's an enormously strong constraint on how many civilizations there could be in the Milky Way. So that's one aspect. I think many people today believe that communication over long distance is fairly doable. It might, of course, be that it's not going to be so much space explorers showing up, but actually it's going to be the robots. So while we might have gone to the moon, Mars is currently only inhabited by robots and doing fine from an exploration standpoint. Maybe we get some humans there eventually, but it looks like we might be sending out more and more post-biological systems. But the interesting thing about these explanations, especially that kind of right-hand side of alienness explanation, is that many explanations require all civilizations out there to act completely the same. And all individuals in all cultures, in all civilizations of all species across the universe need to basically behave the same, which is the strongest sociological claim ever. If you think that actually advanced civilizations undergo a singularity and transcend, then every single civilization needs to do that. If every civilization wipes itself out, then there can't be some peace-loving civilization or civilization that has its act together, which is really odd. And there can't be any survivors that learn the lesson. So it only takes one civilization to start spreading for the Fermi answer to break down. So this is a really interesting philosophical challenge to making a good explanation that works. And of course, every style of answer implies really interesting and uncomfortable things. Maybe we're totally wrong about what can be achieved in the universe. Maybe we're close to the ultimate limits of technology, which sounds very strange. Or it's a very dangerous universe, which is, of course, the topic of this talk. And in that case, other civilizations should be able to observe that it's a dangerous universe. They get the information we have, and nobody is ever helped by noticing that it's a dangerous universe. That's also very odd. Or we converge all on it on something, which might, of course, be interesting if it's also a good thing. Or maybe it's just that we all converge on doing the same bad thing. Maybe you had early civilizations that spread around and are now setting the ground rules. I have a paper called the estivation hypothesis, where I'm suggesting that this might be a reason. You have the great old ones sleeping until the universe get cold enough for the computers to run really efficiently. And right now they have left it to the robots to run stuff. So I don't believe that is the explanation, but it's a fun paper. Or it could be that we're actually, we are the guardians of life and consciousness in this universe, that little single flickering candle flame that might spread or might go out, and it's up to us to decide what to do. Now, one way of trying to deal with this is the famous Drake equation, which is a way of organizing our ignorance, as Jill Tarter put it. So it's a rough estimate of the number of civilizations we might notice in the galaxy. And you take some numbers, you multiply them together, and then you try to estimate how many civilizations could be reachable. It's been a mainstay since the 1960s, and everybody agrees on that. Yeah, this is crude, but it's still a way of organizing it. People's numbers here are all over the place. The first few numbers are fairly well constrained by astronomy. So when Drake and Carl Sagan suggested it originally, they made some guesses, and it actually turns out that the number of stars that form in the galaxy, it's about 7 per year. So that's a ballpark estimate that we got right. The number of planets per star, well, turns out that actually most stars seems to have planets. We are very uncertain about how many of these planets can support life. We get very uncertain about the fraction that has life, and even more uncertain about intelligence, and the fraction that can communicate, nobody really knows. And then there is the length of time civilizations can really release signals. And you basically find people estimating all over the place. So depending on which numbers you select, you can get an answer like 2, it's us and the other civilization, or you're a bit optimistic and you get 50 million civilizations, or you could actually plug in some really small numbers and get 10 to the minus 19. That is, we're the only intelligent life in the observable universe. Now, you can play around with this, and I have a paper that I'm very proud of called Dissolving the Fermi Paradox, where we show that if you actually try to use proper uncertainties, you actually get a bit of an unsurprising result that you can't rule out a really empty universe, even if you on average are very optimistic. Most of the time when people plug in numbers, they say that, okay, I'm making a guess here, and the end result is also a guess. But a guess needs to have an uncertainty range. If you don't tell what the uncertainty range is, it's not going to work very well. But if you do it right, you actually get a slightly reasonable answer that, yeah, the universe might be very empty. But we still can try to gather information from this. And you can, of course, start building up interesting models from this. So one issue is how rare it is to have a planet that is Earth-like or can have life. And there are some people arguing that this is very unlikely, and others are rather optimistic. It could, I think most people these days think that, yeah, terrestrial planets are a dime a dozen in the Milky Way. But life, on the other hand, we really don't know. We honestly have no good theory about the rate of how much life happens per second per liter of ocean on an early planet. It could be that this is something that just spontaneously forms. We know asteroids are full of amino acids, and there should be a fair bit of gunk on most planets. Indeed, the brownish color of the moons in the outer solar system, that is actually because of organic material that has formed and polymerized on the surface. We know that there is water and probably underwater oceans in a lot of places, and life might be splattering from a meteor impact. So it's very likely that bacterial spores have at least once or twice moved between Earth and Mars and Venus when Venus was nicer. But it could be that the probability of life forming in the first place is exceedingly low. There are some good arguments suggesting that the probabilities are astronomically small, much smaller than what you would normally claim. Another possibility might be that life is actually fairly common, but it rarely evolves beyond the bacterial stage. We have a genetic coding system that for billions of years have learned how to photosynthesize and do various chemotropic behaviors, and eventually came up with being multicellular and building nervous systems and taking over the land and the air. But it still took a few billion years. Suppose it evolved at a rate 10 times more slowly. In that case, it would still be bacteria by the time the sun turns into a red giant. And it might be that different coding systems and different forms of DNA actually have different affordances on this. There is another question whether advanced nervous systems are a thing that often shows up. We don't know. I think it's likely once you get multicellular organisms, you need a nervous system, but it might very well be a DNA coding is a bottleneck. So this leads to what Robin Hanson coined the great filter. We know that there needs to be at least one factor in that Drake equation that's super low. And it's probably not the astronomical factors. Indeed, they are forcing the other factors to at least one to be low. So it could be that we have a past great filter, that either there are very few planets or very little life or very little intelligent and advanced life. And in that case, we are the lucky ones. We are the beings that manage to get the going, and now we're fairly alone, but have a universe ahead of us. Or it could be that later terms, how long a civilization remains technological or survives. If that is the factor, if that is the filter, then we're really doomed. There is the third possibility that something really weird is going on, but I'm going to kind of discount that for the time being. The interesting thing here is, of course, that low value of future survivability. That was already noted by Carl Sagan in the 1960s. So when we get to the discussion about the long-term survival of humanity, generally today it's argued by philosophers and researchers on existential risk. But we came in much later than the astronomers. There is actually much more discussion about this by astronomers in the SETI world and to some extent science fiction authors like H.G. Wells. So generally, we know that we are a species among others, and various human species have gone extinct historically. So if we think about our closest relatives, kind of, okay, we're the one surviving species. The Neanderthals, they died out or got absorbed by our species. Homo floresiensis and the Denisovans, we find some remnants of them. All the other hominid branches have disappeared. That's kind of bad news. So when we think about risk, normally we think about probability times impact, but it might also matter how severe it is and the scope. And generally, when I start talking disasters, I'm in the global catastrophic risk corner. Things that are really global and might have really bad effects, and especially across time. I'm interested in preventing dark ages from happening. If there is a nightfall event, how do I make sure that there is a backup of a library so civilization can reboot? What about global tyranny? It might be horrifying and global, but you can kind of live in it, but it's still a bad thing we want to avoid. But the really scary ones are the pan-generational risk, the things that affect all future generations, and that would be like extinction. So what are the existential risks that we can worry about? Well, the astronomical risks are the classical ones. Supernovas and gamma ray bursts certainly are a bit of a mass extinction risk, but it's a surprisingly small one. You need to be very close, within some tens of light years of a supernova, to be really harmed by it. And it's not so much the blast that is the problem as the high energy cosmic rays you get from the nebula. Carrington events and solar flares are scary for us in a technological civilization dependent on power grids that might or might not function after that. But generally, they seem to be rare enough, and with some clear planning, we could actually make resilient power grids. Meteor impacts are interesting because, well, they do happen all the time, and some of them might be larger. It looks like that recent 2024 YR asteroid is going to miss us, maybe hit the moon, which would be spectacular, but it was merely a city killer. Bigger ones that could destroy the climate or cause massive tsunamis or wipe out a part of the biosphere are very rare. And we understand the size distribution so well, so we don't need to worry about it. It's kind of big impact happening maybe every once a few tens of millions of years or 100 millions of years. I think we don't need to worry too much about them. So these are risks that are coming from outside. There are also the risks inside the world, the geophysical risks. As a Swede, I'm of course very concerned about ice ages. I remember vividly when my dad pointed out that where we're living right now, it was once a mile of ice on top of us, and it's going to return. We're living inside an interglacial that lasts some tens of thousands of years, and then it's going to get cold again, and the ice is going to spread out, and then it's going to be 100,000 years of cold again. Were that to happen to our civilization, that would be awkward. But humans survived the previous ice ages. It's just that it's hard to live in Scandinavia during an ice age, but there are other parts of the world you can survive in. Similarly, we have supervolcanic eruptions. Of course, in America, everybody knows about the Yellowstone supervolcano, but there are many others that might have harmed humanity, like the Toba eruption in Indonesia about 80,000 years ago. There is a theory that it nearly caused our extinction. There is evidence for a genetic bottleneck. It's a debated theory, but big volcanic eruptions can really mess up our global agricultural system. And if we want to feed the 8 billion people, yeah, we better keep a watch on that and be ready for it. It's hard to stop volcanic eruptions, but generally most of these geophysical risks are local. Hurricanes are bad if you're hit by them. Earthquakes are really bad if you get hurricanes or earthquakes or droughts. On the other hand, we're having the problem of self these days is, of course, very vivid because we actually do remember COVID. And they have been a cause of massive death over the past. The Black Death, of course, killed a large fraction of the population. The plague of Justinian killed even more. And the Spanish flu, which is, of course, not called the Spanish flu in Spain, but these days the polite name is the 1918 flu. It was a scary peak. You can see in the diagram just how many deaths there were that month because of a mutation of the flu. But obviously humanity survived despite that pandemic. It might seem hard to actually get a pandemic that wipes out a species in the first place because the virus or pathogen needs a host. But there are some frog species that seem to have been wiped out by a fungal infection. So the toads don't die from it. But then we give it to the frogs, and there are several endangered frog species that have gone extinct because of this. So natural pandemics might cause species extinctions. But generally, everything I've been talking about so far is what has been hitting normal species on Earth. And the typical mammalian species tend to survive about a million years. We've been around for around 150,000 years. So statistically speaking, we should expect to be around for much longer. A fairly low risk of dying.
It looks like
Okay,
we just,
did
okay,
did
never
I
mind.
fall out of it?
Yes, you
Okay,
were
I'm
breaking
back.
up. Anders, first of all, your sound was breaking up. I don't know if it's anything that you're aware of. I just tried to send you a chat or can do anything about, but just so you know, I'll try to let you know if it's breaking up. You may want to
Yep.
repeat. Okay.
Thanks. Yeah, I think occasionally comes and goes. I don't know what is making the internet weather here. But anyway, let's see here. Should I return to the PowerPoint and see if
I would
okay.
return to the PowerPoint and
Yep.
go over it again.
Let's see. Yeah. So what was the last you heard me say?
Somebody tell us what the last one was. I was busy trying to chat. It was near the end of the discussion, I think, of that PowerPoint, of that slide.
Yeah. Okay. Yeah. I'm returning to that slide, and then we'll see. Yeah. Anyway, because I want to have a discussion with you guys, so I'm trying to get to the end here of this dreary list. But anyway, the anthropogenic risks are obviously dwarfing the natural risks. And the reason for that is, of course, that we humans are very ingenious at changing our conditions, which is sometimes really good news. We invent agriculture. We can spread to new places in the world. We get a bigger population. Oh dear, we're getting a bit of more epidemics, and even more, we get wars. And we unfortunately haven't figured out ecology well enough, so we might actually cause salinity to grow in the fertile regions because we do irrigation badly. Oh dear. Or we figure out ways of doing organized and mechanized warfare, and that creates the distribution of larger and larger wars. Or for that matter, of course, climate change. And these anthropogenic risks generally looks like very much bigger than the natural risks. The biggest one, the classic one, of course, is the nuclear risk. So the nuclear war risk really made existential threats salient in the 1940s. Back before that, H.G. Wells and the others, they were thinking about that our time on this planet might be finite. We are probably going to go extinct because of natural causes or the heat death of the universe, which made for an interesting philosophical point or an interesting science fiction story, but it was not really something that was expected to happen. And then in 1945, we got nuclear weapons, and people started to realize, oh, we could cause it ourselves. Indeed, as the nuclear arms race got going, people realized that actually, as a side effect of national security, we might be building a world that is dangerously unstable. And of course, in the 60s and 70s, we also got the growing environmental awareness that, oh no, we're messing up the biosphere too. So the realization that humanity is the main risk to humanity became an important aspect. And to some extent, it's a very depressing thought. But it's also a very cheering thought, because that means that it's kind of a political decision whether you press the button or not. It's a political decision whether you make a sensible environmental policy or do nuclear disarmament. This is in some sense under our control. But after decades of the threat of nuclear weapons, we also realize that something being in the human sphere of control doesn't mean humanity is very good at controlling it. So we have this fascinating and chilling challenge of avoiding these disasters. The interesting part about nuclear war, incidentally, is that the biggest threat to humanity was not foreseen when people started developing it. There is this famous story about the Los Alamos scientists realized that maybe we could trigger a fusion reaction that would ignite the atmosphere. And it's true that they jokingly made bets on that at the night of the Trinity test, but they had already solved physics some months ago and kind of realized that actually it's unlikely to happen. But nuclear winter was not a foreseen risk, and it's something that's being contested because it's very dependent on how much soot you get. And even to this day, I'm having arguments online with colleagues and friends about it all the time, which models to believe or not. But it looks like it's a plausible way that if there is a big nuclear war, at least billions are threatened simply because you can't do agriculture. This is where I'm plugging a non-profit I'm involved in called AllFed, the Alliance to Feed Earth in Disasters. We're looking at resilient food solution, like if the atmosphere goes dark because of a nuclear war, asteroid, or supervolcano, how can we make food for everybody anyway? And there are options. There are ways of getting food even in these scenarios. It's just going to require us to start working rather hard on it. The most interesting forms of risk to me, because I'm a science fiction nerd and like high tech, is of course emerging technologies. And this is of course where it gets funny with the Fermi paradox. So bio risks are probably much bigger now than the natural pandemic risk. Certainly nature is throwing things like bird flu at us, but in the lab you can design worse things. I was recently attending a meeting in Washington about the use of AI to enhance pathogens and make scary stuff. And right now, we can't really do anything super useful with AI that is much better than you could do with a library and an evil biotech professor. But it might get easier and easier to build that little biolab and getting help from ChatGPT 7 to come up with something really nasty. Similarly, the concerns about particle accelerators producing strangelets, black holes, or vacuum decay, they seem to be small. There is a little risk there. I have a paper where we analyze it, but it's telling that the risk analysis the particle physicists did was actually wrong. They turned on the accelerators for the wrong reasons. We also have a complex systemic risk, but the big one these days that is keeping a lot of my colleagues busy is, of course, artificial intelligence. Again, long talk just about why do we think super intelligent AI could be very dangerous? Why do we think that even human level or subhuman level AI could be transformative in a dangerous way? And of course, we might make accidental discoveries that later turn out to be dangerous, like the CFCs. They looked like a really good thing, and then we discover the ozone hole. If we had been using brominated compounds, they would have been an even worse greenhouse gas and caused even worse ozone holes. But it was mostly sheer luck that we ended up with fluorinated compounds. So we might imagine that civilizations go through a phase where we invent a lot of stuff, and some of these things are very dangerous, and that might be what kills them off. But generally, when you look at this field, we find that the anthropogenic risks dominate, and the technological risks are much harder to predict than wars. But also, we can design ahead. We can realize that super intelligent AI is probably a dangerous idea unless we solve AI safety. We can work hard on AI safety, and in a sane world, we would be very good at it by the point our machines start talking back at us. There are various risks that combine them. But many of these ones can be fixed and be survivable. We can build survival shelters. We can put seed banks in Svalbard. We can actually stop at least the ozone hole. We've been somewhat bad at handling climate change, but it's worth noting that many of these risks are being managed fairly well. So this leads to this interesting link of the Fermi paradox and existential risk. The idea of technological adolescence, it might actually be a common thing. Carl Sagan suggested that most civilizations grow in power, become powerful, and then destroy themselves. But maybe 1 or 2% survive. But if that happens, it's not a good Fermi answer. The other civilizations or the survivors, they dust themselves off and go off to build glorious things and maybe having learned the lesson in a good way. The really interesting thing is, however, that maybe the risk of going extinct is never zero. after all, even if we have our act together, we might still be unlucky that there exists some obscure physics effect that if you try that one out, your planet explodes. But there might be a way out of that, and that is, of course, if you spread it. So this is where we get to the idea of meta-populations in ecology. So if you have a population like butterflies living in one single meadow, if they go extinct there, then they're gone. They can't recolonize from somewhere else. But if you have butterflies living in different meadows and then very rarely moving between them, if one of the meadows goes extinct, it gets recolonized by the other meadows, and suddenly you have a much more stable population. So this is called a meta-population. I think this is also the most realistic way of actually surviving long-term in the universe. You would spread out. Doesn't necessarily mean that you have to spread very widely, but already not being on one planet reduces the risk a lot. Now, going to Mars might not be a cost-effective way right now to reduce our risks, because there's plenty of stuff we can do fairly easily on Earth. But many of the technologies you would like to have if you want to settle the solar system, like really good recycling, automated mining, and solar panels that are really effective and can be built and deployed in an automated way, automated closed ecosystems, would also make Earth much more resilient. So I think in general, if we believe that existential risk is a mere constraint, we would expect that surviving civilizations would tend to spread out. And that, of course, makes the Fermi problem a bit trickier. One way out of this is, of course, to think that if we start spreading over vast distances, how large could those distances be? And I have some papers where I look at how far we could spread between galaxies. Most discussions about space settlement are about the solar system or the Milky Way, but if you can settle the Milky Way, the other galaxies actually look pretty reachable if you have a somewhat fast spacecraft. And it turns out that if you can go at some fraction of the speed of light, you can reach literally millions and billions of galaxies, at least if you can use post-biological technologies like nanotechnology and AI and the uploads to go there, and then maybe build biospheres. And basically, it looks like if somebody is spreading out, doing like that, you get a kind of phase transition of matter from matter that is just sitting there to matter that intelligence and life can transform into whatever it wants. That might very well be that we leave it pristine and just keep the universe normal, or it might be that we spread life and intelligence into everything, or convert every chunk of matter into a computer running the happiest mental states we can possibly imagine. Another interesting observation here is that we're obviously living before this transition. We're living in a universe that right now looks pretty inert. We don't see very much. And it might be that it's rare that you get civilization that starts spreading out. Robin Hanson suggested that we could call the ones that don't spread the quiet ones. And they don't make history. It's the grabby ones we should look for, the ones that want to go out. So in his model, you have various rare places where intelligence starts spreading out. And it still takes a long time to spread over billions of light years. But eventually, all parts of the universe is being influenced by intelligence. And we're living before this transition. And for various reasons about evolutionary transitions, which I'm not going to get into, we might believe that we're fairly close to this transition point. So when you run the numbers, you end up at between 50 million, we might meet aliens within 50 million or 50 billion years, which might sound very far in the future, but it's actually quite a small amount of time when thinking about the history of the universe. So in this model, we might have a choice. Do we just sit here and wait until we get steamrolled or hopefully find the alien friends? Or do we start spreading out to get our little part of the universe and do whatever is good with it? Now, that causes interesting ethical questions. So my conclusions is that I actually do think that the answer seems to be that we're living in a sparsely populated universe. I don't think we're alone. I think there are aliens out there, but they're far away. And soon, by cosmological standards, it's going to be very settled. The good news is that this model means that the stars are not foretelling our doom, but we still might be in a sticky situation because, well, we are the stupid humans, we're not very wise, and we're still living on one planet which is pretty fragile, and we might want to do a better job on handling that. Well, that was my talk. I'd love to hear your comments and questions. Thanks.
Thank you very much, Anders. There's so much here that various people, I'm sure, have their questions. So I would like to open it now to the floor for any questions, and you can just pop in with your questions if there are too many. Oh, raise the hand. I guess that might help. Raise the hand, and you go to reactions, and let's see. My reactions. Oh yeah, raise hand. So you can see the person and then you see the hand. You see that? I just did it with mine. Christopher Merle, do you have a question?
Yeah, I had recently read about the grabby aliens, and that one, yeah, that one's probably one of the more interesting hypotheses that I'd heard about, and I'd like to know a little bit more about because to me it seems like we might be the grabby aliens if we're the first ones, just given our at least the European history of colonization of the rest of the world, um, and that might be something that we might be the ones that become the grabby aliens. But yeah, but I agree that I do believe that there are aliens out there, but that they're very sparse. But so anyway,
Yeah.
but if you could elaborate more on the grabby aliens.
Yeah, so the Robin's theory has kind of several parts, and it's very funny because Robin and me have been talking about this for ages, and I had all the pieces literally in my own big manuscript for a book I'm writing, and I didn't put them together before Robin, so he kind of totally scooped me, which is awesome in many ways. So the first part is observing that you can spread over these vast distances. So in a paper I wrote with Stuart Armstrong, we looked at if you use a small Dyson sphere in the solar system to just send off spacecraft, how much sunlight do you need to settle all the reachable galaxies? And we realized you need about 6 hours of sunlight to send off probes to all the reachable galaxies. And then they might build the Dyson spheres over there and send off probes to all the stars. So you essentially just do 2 steps and settle a very large chunk of the universe. Now, and of course, aliens could do that too. So our point in that paper was we just made the Fermi paradox 1,000,000 times worse, which is of course typical for when the philosophy department gets involved in any question. We make everything worse in a profound way. But then Robin and me started talking about, okay, how much do we expect that the universe can't get completely settled? And it depends on how sparsely inhabited it is. If we're the only ones in the observable universe, we can go off very far, we never meet anybody. If you're below a certain level, every in a galaxy is going to get visited by somebody. Now, of course, there are going to be these civilizations that don't go anywhere for their own reasons, but some of them are grabby. And grabbiness doesn't necessarily mean that they're nasty in any way. It might be that we all want to have nature preserves or want everybody to be friends, but some of them might be problematic. There is a very interesting question, which aliens you want to be neighbor with. But the really interesting question is, when should we expect civilizations? So we have this weird situation that we're simultaneously late and early. Earth was one of later planets to form in the Milky Way. And if you predict the number of stars and planets that form across the history of the Milky Way, we're kind of after the peak. So there are many older planets around. So you would expect that actually maybe there should be a lot of older civilizations. But if it's very hard to evolve to be an intelligent being, there are several hard steps. You should expect most intelligent beings to come into existence relatively late in the history of a planet. We might just have had an unusually quick evolution. And of course, you get a kind of weird selection effect, because if it's very rare that you have the time to evolve something intelligent on a planet before the sun turns into a red giant, then the few planets that are lucky, those aliens are going to have really warped probability estimates because they were actually ridiculously lucky. They're not representative of most planets, because most planets are just full of bacteria who don't do any mathematics and don't care about the Fermi paradox. So Robin plugged that into his model, and that is why he thinks we're close to this transition. Now it's interesting because I'm more pessimistic than Robin about the probability of life in the universe. I have another paper where I did the numbers. So I end up thinking it's billions of years in the future when in a galaxy far, far away, we finally get to shake tentacle with the aliens. While Robin is open that there could actually be almost next door. Indeed, he has been rather unfazed by ideas of that the UFOs might mean that the aliens are already here. Again, a fun thing to debate. Okay, that was kind of my attempt at summarizing the grabby aliens model. It's a very nice one because you can play around with the parameters and see what you think works and what doesn't work with your experience.
Thank you.
John, you have your hand up.
Yeah, I was thinking, what if the reason we haven't had much contact with advanced civilizations is that we're the endangered species, and they have laws protecting us, and so this whole sector of the galaxy is sort of cordoned off so that we don't get panic about
Yeah.
like that we're this little colony of 8 billion and there's like quadrillions of intelligent beings out there, and we believe we're so important it would just their psychologists say it would just wreak havoc with our society, and so they're introducing ideas slowly. It's also possible that there are some that want to would like the iron core of the earth is valuable on the galactic market, but they can't just cut open the earth and take it. I mean, they have the tools to, but so first they have to somehow inspire us to move to Mars, and then after we most of us have moved to Mars, then they can take it.
Yeah, so these are versions of the sewer hypothesis. I think it was David Brin who actually coined it. His paper on the Fermi paradox from the 80s, by the way, is one of the best ones. He's not just a good science fiction author, he's actually a really good SETI researcher. My problem with that is, of course, well, there's bound to be some alien teenager who wants to mess around. Can you really enforce keeping us in the zoo? And of course, one funny answer is, of course, actually those UFOs, they're actually alien teenagers annoying the rangers all the time by trying to buzz us with the little UFOs. But I think the bigger problem with the sewer hypothesis is that the rest of the universe doesn't look very industrialized. It looks very much like the natural process going on there can be explained by just normal natural processes. There are a few weird things, but nothing looks particularly artificial. I would imagine that the animals at the zoo would notice that the skyline looks very different from a forest. So there is that problem with making the zoo hypothesis stick. My estivation hypothesis is a bit similar. There I assume that the advanced civilizations are sleeping in, but we left the robot rangers to kind of keep an eye on the galaxy. But I would expect that to lead to two predictions. One is processes that really waste resources for an advanced civilization in the far future would be inhibited. And we don't see that much of the inhibition of that. And second, if we were to try to do something that could mess up the galaxy for the sleeping great old ones, the rangers would really want to intervene. So one way of testing it is to try to unleash, let's say, self-replicating machines to spam the universe. If that happens, then you would expect the robot rangers to show up if they exist. But it might be a rather dangerous way of testing it, because maybe that is the signal, okay, let's swat the solar system because it's gone bad.
Also, I think John Ryder, is it? John Ryder had in the chat, he was asking about Olaf Stapleton's Last and First Men and what you assessed the value of that.
Yeah, I really like Olaf Stapleton's Star Maker. Last and First Men is an amazing novel, but Star Maker is the novel I'm always telling people about when they ask, so what's a good science fiction novel? And then, of course, I have to warn them that, yeah, it's also a science fiction novel from 1930 that's more like a philosophy lecture than a novel, but it's still astonishingly good. And I think the cool part about Star Maker is that it's throwing all ideas simultaneously at the wall. in a Staples universe, you have all sorts of reasons why civilizations don't make a mark, like disasters. Everything is blowing up or dying for all sorts of internal or external reasons. But he also got interstellar empires. He's got these vast time scales, which means that things can happen, and then billions of years later, there is not much of a trace of them. And simultaneously, there is a progression in his model. He's fairly optimistic in many ways that actually intelligence and consciousness does advance across the history of the universe. It's just that maybe it's not enough. Maybe this universe is not perfect enough to actually reach the heights it ought to do. Now, I was very taken by that novel when I read it as a child, and it honestly affected a lot of my thinking about these things. I wanted to make sure that we can get a universe that has that kind of epic history. And it's an interesting question also, what could hide the far past? A webcomic I'm very fond of is Schlock Mercenary by Howard Taylor. It's an epic thing. It was produced one strip each day for 20 years. And while it starts out as a kind of humoristic military space opera, gradually it gets a plot. And in the later third of its run, suddenly the Fermi paradox comes up. Because in this galaxy with a lot of aliens and things going on, there are actually no really ancient alien civilizations. And they start to actually do a bit of archaeology and realize there is some evidence that there must have been other galactic civilizations before ours. Over billions of years, there have been other galactic civilizations, and they're all gone. And that is extremely creepy, especially since they're fighting a war against certain entities from Andromeda galaxy, and it's not going terribly well. I'm not giving anything away, but again, there is this wonderful scope of time here. The idea that actually, if a civilization goes away and another one shows up a billion years later, it might be hard to even notice that it was around unless it done some really impressive mega-scale engineering. There is that star that got the nickname Tabby's star, but had these weird things obscuring it. Nobody really knows what to explain it with. It's most likely some kind of dust or comets. But of course, everybody was suggesting that maybe it's a Dyson sphere or remnants of a Dyson sphere. And since I've written about Dyson spheres, people started asking me questions. So I did some calculation how long a Dyson sphere hangs around if you don't maintain it. And the answer is about 100 years. Because then meteors hit it, fragments move out, they hit other parts of the Dyson sphere, and you get this exponential Kessler cascade of everything hitting everything else. And then you have a dust cloud, which then in a million years turns into planets. So the probability of seeing a decaying, romantically broken Dyson sphere over its life span is very small. So it doesn't work very well to explain Tabby's star. Similarly, maybe it's a Dyson sphere somebody's building, but the probability of seeing it being built is also rather low because it probably just takes about a century to build it. Unless, of course, there is cost cutting and some bureaucratic problems, etc., which again makes for a good story.
Okay, well, I see 3 posts from Bob McMillan there in chat, and if you'd like to address any of those, he's putting out things and they're not phrased as questions.
Yeah, I think the Jehovah's Witnesses point is important, actually. Ethical reasons might be very strong. So if you imagine that you're finding aliens out there and they have a philosophical view that's fundamentally evil from your view, then you might want to use resources to try to stop them. So my standard example, and this is usually fun in Oxford because I always have a few negative utilitarians in the room, is of course that negative utilitarians that think that suffering is the worst thing ever, they might want to remove your resources if you don't care too much about suffering. So if I'm filling the universe with rainforest and the civilizations, but some animals and some people are unhappy, to a negative utilitarian, that's the worst thing ever. And actually, they need to stop me from doing this. So they make very bad neighbors for my philosophy. So there are various philosophies that don't get along. There might be others that just naturally have a live and let live. But generally, there are many reasons why you might want to deal with an alien civilization. So I do think that it's hard to run the zoo hypothesis. Then, of course, the really interesting thing is if you meet the aliens, you might want to check what's your theory of ethics. Have you discovered something we have totally missed in our species? It may be the true meaning of the universe can only be discerned when you talk to enough alien civilizations. Okay, I see Christopher and John also got hands up now.
Yeah. I wanted to go back to the Drake equation. Considering how the number of astronomical discoveries over the past few decades, especially with Kepler, the number of planets, and also possibly with JWST, how much do you think it's our better understanding of what we see out there has refined the Drake equation?
The first few terms have definitely been refined. I still think we're slightly uncertain about the planet and star formation rate because it also changes. It's a bit like the weather, but it's about between 1 and 10 stars per year. When it comes to planets, basically we're getting spammed by planets these days. It looks like most stars have planets. It's just that we used to believe that our solar system was representative and normal, and now it looks like it's actually unusually lacking hot Jupiters. Partially this is because it's easy to detect hot Jupiters, so we tend to notice them, and it's much harder to find terrestrial planets. But it looks like many solar systems are much wilder than ours. And of course, that means that the rare earth people have a good reason to say that, look out, maybe we're living in an unusual, it's not a rare earth, but a rare solar system. The James Webb Telescope, I still haven't seen the really latest data, but I think we're going to get a deluge of extra planets here. And we're probably going to refine the corners of a diagram of size and distance from the star that we're bad at right now, which is going to be interesting. To me, the biggest surprise was we got so many super Earths. The Earth-like planets, or maybe in the life zone, but with heavy atmospheres, or most likely very deep oceans. Ocean worlds were something that kind of classic in science fiction, but not taken that seriously. Now the question is, Robert, why is Earth so dry? It might have been that collision with Theia that created the moon also dried out Earth. We actually got way less water and volatiles on Earth, which is the reason we're actually land living.
Okay, I see John Ryder has his hand raised.
Yeah, I want to ask, and Larry Niven, I think in his book Neutron Star, tossed out the idea that interplanetary space is different than interstellar space, and interstellar space is different than intergalactic space, and that these are different mediums, as different as water from air, and that all our speculations about speed of light and what else can be done are based on what we see of our interplanetary space, and that it could be completely different once we get outside of the get past the Oort cloud.
Yeah, I don't think that idea has aged that well, but we certainly know much more now about the different spaces, and they are different from each other.
Yeah.
So interplanetary space, you get a fair bit of dust and stuff, and the interstellar space also has a surprising amount of dust. And this is one of the big problems for me when I'm thinking about my relativistic spacecraft, because you don't want to run into a grain of sand when you're moving at 99% of light speed. Then that detonates like a little nuclear bomb. So in a lot of the calculations I have been doing on interstellar settlement, the main issue is how much armor do you put up ahead of a spacecraft? You might have aluminum foil, Whipple shields, and lasers to shoot down things, etc. And in really dusty or rather grainy parts of a galaxy, it might actually be rather hard to move fast. So spreading inside the Milky Way, it might be easier to go above and below the plane. We're right in the middle of the plane, but going along it might actually have too much dust and grains. Inside a solar system, typically you're not assuming light speed distance. The intergalactic space is interesting because on one hand, you get much less dust. because the dust tend to dissolve because it's so hot gas out there. The gas is literally millions of degrees, but it's also ridiculously rarefied. But it seems that it tends to erode dust grains. This is great news. It's really effective in getting rid of that. So traveling, if you can travel between the stars of the Milky Way and can survive long enough, then you can go to Andromeda. But the bad thing is, of course, the erosion from the hot gas might actually be an interesting issue, especially if you're moving close to light speed. That hydrogen gas is no longer behaving like gas. It's behaving like a proton beam hitting your spacecraft. That's not nice at all. So
Okay,
yeah, there is an interesting problem there.
okay, we have a question. Hugh Hudson doesn't know how to do his hand raising, and I'll just say for everybody, in case others are in that situation, you look at the bottom under reactions, there's a button called reactions. And one of the choices is a little hand, and that's your hand you can raise. There you go. Okay.
I thought I tried that and it didn't work. Anyway, so I had a question just for more clarification. I thought that I detected some optimism about global warming, or not some lack of extreme pessimism about global warming, and I'd like to. And I also noticed that in this Kim Stanley Anderson book, The Ministry for the Future. Are there reasons to be optimistic, do you think?
Oh yeah, oh yeah. So I think the political side of dealing with climate change, that is sad and makes one pessimistic. The technological side, on the other hand, we seem to have passed the tipping point towards solar power. Solar power is getting cheaper at such a high rate right now, but the fact that there is still subsidies are getting cut doesn't matter very much. It's actually cost effective to put in a lot of solar power in many places. Even if you're a rabid climate change denialist, if you care about your budget, you just realize, yeah, but it's still stupid not to put up solar panels. Renewables are getting really good. I'm also very happy with how the fracking industry accidentally helped develop very good new methods for geothermal power. Previously, geothermal power was always very localized and you couldn't run it very in a large scale, but it looks like we can actually scale this up quite a bit. So that technical side is doing really well. And for all his faults, Elon Musk was onto something. Once you start electrification of more and more systems and building better power grids and making economies of scales for batteries and solar, you keep on rolling downhill there. The issue is, of course, that, yeah, we still have that darn carbon dioxide in the atmosphere, and it's still going to mess up a lot of stuff. Now, I'm not thinking that that's necessarily the end of the world. When people say that, 3 degrees of warming means the end of humanity, I generally roll my eyes. I've been in a big Twitter debate about trying to find good evidence for catastrophic ecosystem collapse. And generally, it's just that it's a bad thing, all things considered. The coral reefs outside this island are getting bleaching. I talked to somebody who was planning to we need genetically modified corals to keep the coral reefs working. And many conservation biologists are kind of screaming at that idea. But if the alternative is no coral reef, I think actually we might need to do that. Now, the interesting thing in the Ministry for the Future is that is a story about how people get their act together, and then you basically have democratic governments setting up the right technocratic solutions. The other one is, of course, the bottom-up solutions. Solar panels, when they become cheap and sensible, everybody puts them up. Maybe you can create incentives for carbon capture and storage. We're not terribly far away from it being cost effective, but that probably requires centralized solutions. So I have a feeling that we might muddle through the climate situation. It's going to be a mess, but it's kind of a survivable mess. The problem is the unsurvivable messes. For a while, it looked like there was some probability that we could get 10 degrees of warming. That would have actually been really dangerous for humanity and a lot of other species. But the probability of that, given the latest understanding of climate, now that has gone down significantly. That's less problematic. But we still have to deal with the systemic risks. In a world where you have rising water levels and hurricanes and occasional agricultural failures, and we're all interconnected, and there might be geopolitical tensions and transformative AI and biotechnologies that are hard to control, that might still mean that we get a systemic collapse not because of climate change, but climate change added extra tensions to a system that was already under stress. That is probably what worries me the most. And it's tricky because we don't know how to deal with systemic risks very well. So this is one of the big research topics I'm doing at my institute over in Sweden, actually.
Well, thanks. But it isn't just global warming, of course. It's evolutionary change. The biology that's this rapid changes that we're imposing on the Earth.
Yeah.
So
If they were slow enough, I don't think it would be a problem. So during the Eocene, there was a spike of temperatures that was probably up to 12 degrees of warming in the polar regions and 3 degrees of warming at the equator that lasted for about 200,000 years. You got all sorts of interesting evolutionary changes, but the onset looked like it took about 2,000 years. That might be enough to not cause a mass extinction, but you did get these cat-sized horses and a lot of weird adaptations. But we might now be changing things a bit too fast. Or maybe it's our job to help the biosphere in that case update itself fast enough.
okay, thanks.
May
Thanks.
I ask my question?
Yeah, sure.
We live, my husband Bob, who is present here at the meeting, and I used to be my son. He's here too in California. All lived in the Sonoran Desert. We still do, and he used to. And there are plants that with no watering thrive here, and they don't conk off until way into the summer when it's 110 or higher. And one of them is called London Rocket. It's a variety of mustard. And in most places you see it, it has a little flower way at the top, one long stem with 4 or 5 little tiny flowers and very green serrated leaves. And I looked it up. I've been studying it intensively. It was very much in North Africa and Mediterranean Sicilian cooking considered a very valuable part of their diet because it can handle these very, very hot temperatures without any watering at all, even in a desert. And I was thinking of, modifications that could be done, taking it further into the Sahara, right at the edges, bringing in London rockets, because they will take the carbon dioxide and create oxygen as well as feed people. So this kind of thinking of plants that survive in a seriscape, a very dry and hot place. Have you done any studies on that? It has two folds, both agricultural for food and putting more oxygen.
Yeah, that's wonderful. I didn't know about this particular plant. So what we have mostly been thinking about in Alfed is the cold scenario when you get a nuclear winter. So Dave Denkenberger, who might be a very fun person to invite to lecture about this, he wrote a book some years ago, Feeding Everybody No Matter What, where he looked at all the different options. And indeed, the cellulose is, after all, a carbohydrate. It's just that we can't digest it, but we can find ways of converting that into stuff that fungi or insects or cattle could live on. We have been looking at using kelp farming. We have been looking at methods of actually using natural gas and other things to get bacteria, so you can then feed that to animals, etc. But that is on the cold side. I think we haven't studied the hot side enough, and I think there's many interesting options there. An overheated world is still, unless you get a ridiculous level of overheating, a world with quite a lot of biological productivity. And life will kind of find a way, and humans are good at figuring out ways of eating what is available. But finding the right things that are both giving us food and absorbing carbon dioxide, I think that is where we need a lot more thinking, and I really look forward to reading up more about this plant.
I will send you the article, just the what do you call it, the scientific species name and everything. And there are already articles starting mostly about it as an unused, where people use the word weed, the insult word. And large parts of the world see it and they rip it out of their gardens. But in these very arid places where it gets very hot, it has for centuries been part of their diet.
Yeah, yeah. I'll really look forward to read up about it.
So any others with thoughts or questions for Anders? I want to say one thing. This is the most tightly packed, substantive talk I think I've ever heard in several years of doing this. It's very hard to, so many topics. You truly are a Renaissance person.
Yeah, I'm doing my best. I'm just the kind of student who really annoys professors because I want to read everything.
Mhm. And that's another aspect, don't you think, silo vision? Because people are so specialized in our higher education programs, and you're one of these, and I tend to do that as well and irritate people, jump out of one silo and look over the wall into some other field.
Yeah. And generally, that is my trick. I don't think I'm a particularly brilliant philosopher or computational neuroscientist or geologist or whatever, but I'm able to talk ethics with geologists, and I can explain neuroscience to philosophers. And by jumping between silos, you get an extra bonus. And I think that is a very fun trick. And this, of course, also goes for writing fiction and art and many other things. Once you're out of a silo, yeah, it might be hard to place you, but you get a lot of very fun opportunities.
We are the connectors. And I see Shay. Shay, what would you like to ask?
Thanks. You mentioned the feasibility journey that solar has been on and how it's at a tipping point now where it's more affordable and available than ever before. I'm wondering about Dyson spheres and what it would take to get us to that point with Dyson spheres.
Yeah, in some sense, we already have a very small start of a Dyson sphere because we actually have satellites in solar orbit that are powered by solar panels. It's just that the total area of a current human Dyson sphere is probably the size of a smallish house. The problem of building a Dyson sphere is that if you really want to grab all the energy of the sun, you need an enormous area of collectors, and you're not going to do that with a single factory. You need some form of self-replication. So there is a Canadian engineer, Alex Ellery, who's been working on self-replicating robots, actually looking into how to actually build them. And he's mostly interested in using them on the moon to turn moon dust into solar panels. And then the idea is that then you can use antennas to radiate the beams of energy over to Earth for use or to spacecraft. And I think that is the way of doing it. You want to use self-replicating factories. So I've been working out details in more and more detail. And my recommendation would be to have these robots mine asteroids, turn that into solar panels, robots, and factories for making more solar panels, robots, and factories, and occasionally transport that to another asteroid. A lot of it depends, of course, on what kind of Dyson sphere you like to build. If you build it out of current photovoltaics with silicon, you need quite a large mass. You need to probably disassemble Mercury, which is what Stuart Armstrong and me did in our paper about settling the universe. We hand-waved a few of the technical and mining details there, I must admit, but that you need a lot of material. But you can also make solar sails that are very thin. If you take aluminium foil and make it thin enough, it's going to hang there because solar gravity is pulling it towards the sun and the light pressure is keeping it lofted up. If you make it half as heavy as that, then you can make a parabolic reflector that is a statite. It hangs there, it reflects sunlight onto a little black body that gets heated up. And then you have a little stem where you put your heat engine or some Peltier element to get electricity. And on the outside, you put a radiator that radiates away the heat. And these ones would have to be very light, but they could just hang there in a sphere. And when you calculate how much mass you would need for that, you would need essentially the mass of Ceres and I think one of the other big asteroids. The total amount of mass is minuscule compared to the rest of the solar system. And also you don't have to disassemble planets, which probably tends to upset neighbors quite a bit. So that, on the other hand, would require pretty finicky technology. You would probably want to use nanotechnology for it. Indeed, my old friend Eric Drexler, the father of nanotechnology, he got in on this whole thing about nanotechnology when he was trying to design solar sails. And he realized that a good solar sail is really thin. I need to make it in space because we'll always break when I do it on Earth. And what would it take to make a really thin solar cell? What's the thinnest one? And then he realized that molecular manufacturing was the solution. So then he handed over the solar cell stuff to some of his colleagues like Matloff and started working full-time on the nanotechnology the topic. So I think we're right now kind of in a very primitive stage. But that's fine. We are still not even exploiting the solar capacity of all the built-up surfaces we're having in our cities. Once we covered every rooftop with solar panels, then we're probably good enough at making cheap solar panels to start thinking about what to do on the moon. And once we're good at that, then we can start thinking about how to set up the factories along the asteroid belt. And then, of course, there is an interesting coordination problem of setting up traffic control. You don't want the solar panels to shade each other too much. You want to make sure that nothing collides, etc. And you might want to have an energy sharing agreement about what you're using the energy for.
Yeah, thinking about solar panels, you can have energy generating solar panels, or like you mentioned before, you can have kelp growing panels that are solar based, but not for energy generation. They generate biofuels or spirulina kind of food or any number of other things. But the idea of covering
Spirulina
our
is
buildings
awesome.
and plants is an interesting one for future
Oh, yeah.
thinking.
Yeah, you can imagine a very green Dyson sphere where instead of the normal solar collectors, you have these sheets where you circulate water and algae. I've been to an algal farm in Sweden, and it was amazing seeing these almost black tubes full of spirulina algae producing so much nutrients. And of course, an actual Dyson sphere is probably not going to be homogeneous, one kind of thing. It's just that it's the easiest way to hand wave around. In practice, I would imagine an advanced future human civilization to have this vast set of mixed things. There might be O'Neill habitats, there might be solar collectors, data centers, there might be these algal farms. There might be very strange things in the outer part of the solar system. You also want to radiate away the waste heat. And there is a lot of ice out there that you might want to build ice-based technologies on. I'm actually very big on low temperature technology and very curious about how much robots you could actually literally build out of ice that you dope with different chemicals. It might very well be that the Dyson sphere has several layers. My old friend Robert Bradbury, who coined the term Matryoshka brain, had this idea that you had several layers like in a Russian doll. And it turns out that from an energy and entropy standpoint, his model is not optimal. But I think in practice, from an engineering standpoint, we might actually have concentric layers like an onion on a Russian doll, and different parts of the sphere doing very different things. And all in the middle of it, of course, you might still have Earth orbiting, and we all have a treaty that all the collectors between Earth and the sun have to tilt whenever Earth is passing by, so Earth gets enough sunlight.
Well, if I had to characterize all that we've been presented in this amazing talk, I would say that for all the risks, we've been given a lot of hopeful things to go with those risks and other ways to looking at it or other ways to approach it. And we hope to have you back. I've had some repeat speakers, and I think you're a good candidate to come back.
I'm very happy to be back in the future. If I can give you some existential hope, I'm very happy.
And you have. One thing I would like to request is you mentioned a few papers throughout your talk that you have written. If you could just give a list of maybe 3 or 4 of these relevant papers, I can put it out with the next notification to our members.
I'll do that. Yeah. I think I have a few that might be fun. And in many cases, when I'm writing papers, I'm thinking maybe this is not the best academic paper, but it might be useful for a science fiction author somewhere.
Oh, sure. That's what science fiction ideas are us, as they say.
Yeah.
Okay. Well, if there are any final comments and applause, congratulations to the speaker. Otherwise, we'll wrap it up.
Well, thank you so much.
I think Hugh is applauding, and we're all applauding. You can't see it.
Yeah.
We're all applauding. Thank you so much, Anders. And I will be sending you one of my artworks. I'm going to give you a prize for such a good talk.
Oh, thank
I'll have
you.
to look through them. It'll either be astronomical or microbiological, one of my little artworks. Thank you very much. And
Thank you.
again. And
have a wonderful weekend. Cheers.
Cheers to all of you.
Bye-bye.
Thank you. Bye.
Thank you.
Bye-bye, everyone.
Thank you.
Bye.
Bye.